Now let's have our next speaker, Professor Antonino Marciano. Antonino is a current associate professor at Fudan University, full professor for the Italian Ministry of University and Research, and a member of the Italian Institute of Nuclear Physics. Please join me in welcoming Antonino.
So thank you again to everyone, and thank the organizer for having me here. Thanks to Filippo and Costas and to everyone. So today, I'm going to talk about, let's say, the link, a way to bridge artificial intelligence with the quantum world. One of the way to think about this this bridge, which let's say is a new link, has been delved recently in the literature, and in particular, I'm going to focus about a model I am concretely working on together with Filippo, and let's see, there is a paper with Filippo and Costas and the collaborator of ours that we publish on the Journal of Neural Networks, which is at the base of most part of the thing that I'm going to talk about. And so just a couple of words about me, but actually, it's been introduced already. So, let me skip this eventually because it's not as much as important. Let me start talking about, let's say, the difference between the classical and the quantum world. So, let's say that there's many points we could tackle. This this difference, but eventually, it's the main one is related to the discreteness versus the continuity, and in particular to the wave behavior of quantum matter. So that's why, since it's described by equation, which is a wave equation, we have a wave function that describe a system, a quantum system. So any system, then any, let's say, particle is has a nature which is discrete, but has also nature which is a wave, and so it's described by a wave function. And this is the first element that we have to introduce when we talk about quantum mechanics. The second element is the superposition principle. So the fact that and this is purely quantum as well. And the fact that we have always to superpose two states, so possibilities. So, for instance, we know about the poor Schrödinger cat, is half dead and half alive. But this is only the most simple example that we can consider. There is another example that we may think about, which is actually spin. Spin is, let's say, a particle with a certain angular momentum, intrinsic angular momentum, which we can think like an arrow, which can be directed up or down, okay? And in this case, up and down are the two possibilities. Of course, then we can have, let's say, other system in which the space, the Hilbert space of the possibilities is much, much larger. And in that case, we're going to have a superposition of all these elements that can be considered. There is also another point that I want to talk, mention. There is another point which, of course, has to do with a combination of the two ingredients that I gave it to you. So one is the superposition, another one is that the wave function. And the point is that if you may also consider product of states, and you may also consider entanglement, which is another feature of a quantum system. Entanglement is basically something which is not clearly only a superposition, but is a superposition of product of states which cannot be separated, cannot be disentangled. Okay, and this is also a particular feature of quantum mechanics, and let's say that the history traces back to something extremely interesting, like the Einstein-Podolsky-Rosen paradox, that basically you can measure a state, and once you measure a state, even though the other one has been flying around away from the first state that you measured, you know automatically what is the measure on the other state. That means that correlation in quantum mechanics are not local. Okay, so there is non-locality. So whenever we have to consider a path in quantum mechanics from initial to final, from birth to death, we have to sum of all the histories because of this, let's say, axiom that I'm trying to spell out in a very simplified way. And so this sum of all the possibility is what we call the path integral, basically. We have to consider everything because we have the superposition that act at every point. And this also can be understood in terms of the Heisenberg uncertainty principle that tell us that we cannot have the highest possible precision on both the measurement of position and velocity of a particle. That means if you know very well where is a particle, you don't know very well what is the velocity. If you don't know very well the velocity, even classically, you don't know where the particle will be. That means that you cannot know where the particle is with certainty. You only have some measure of probability. That means that at the end of the day, you cannot know what is the path. Classically, you know what is the path, but I mean, we don't know what is our path from the birth to death. So that we have to sum up all the possible histories. And now, I mean, it's like, let me go back to the main ingredient. So we have the classical torque versus the quantum bit. So a classical bit is up and down, but a quantum bit, because of superposition, can point everywhere on this sphere, which is the Bloch sphere. It means also that, I mean, there's much even more information that can be encoded here, because of course you can represent basically north and south of the hemisphere with a classical bit, but you can represent a point on the Earth with the quantum bit, if you think about that, because it has two angles that vary in a continuous way on the sphere. So, I mean, now let's go back, or come finally now, where we talk about artificial intelligence, and in particular, we can focus on neural network architecture. And by this association that I've been talking about, now going from the classical to the quantum, it means that basically we have to associate some nodes, which are the entry data, with some numbers that now are numbers of some operators. So they are what we call representation. And input and output data are mirrored in this picture that I'm considering as the boundary state. So birth and death, okay? And then, I mean, it's we will have another ingredient which is very important when we want to mirror quantum mechanics with artificial intelligence, in particular with some structure in your network structure architecture, is basically to consider that we have entry data that are associated to nodes, and these nodes in a standard architecture are just nodes that are disconnected. But the idea, which is the idea we've been pushing forward recently, actually over the last years, is that these are actually interconnected, even this node. This interconnection create basically the support for a topological discussion. Topology is a beautiful word that comes from Greek. Is the study of the location, basically place. So basically, the features that, I mean, it's a manifold, which is the place where things are happening, have, without taking into account metric properties, are the topological properties. So, for instance, if you have a cup, for a cup, let's say there is a topological property, which is basically I can deform this cup into a sphere. Okay, but if I have a cup with a handle that I don't have here, would you have that the topology is the same one of a torus, which is also donuts? Okay, and then, I mean, you can think about other properties like twisting and so on. So now we're going to use this, and I mean, it's, we immediately coming to the point that, I mean, we can have knotting, and this knotting is in a way to encode information, because, I mean, you can deform the manifold, you can deform the space, you can deform the way in which the space is twisted, and this is a way to do encoding of information. And why this should be interesting? Well, because this topological encoding of information is very much stable, and this will be clear in a while, but actually I can spell it now, even now. The point is that through this bridging artificial intelligence with quantum mechanics, we are automatically creating a bridge with some material, which are topological material. And this topological material, we are able to create some topological invariants which are stable under, let's say, noise, which is created by, I don't know, cosmic rays, by your heat when you come up with your cup of tea or coffee close to an experiment, or radiation from your cell phone, and so on. So you need something that should be stable. And this topological feature, this topological structure are stable enough, and also fault tolerant. Then, I mean, these are useful way to encode the information. And now we can think about what is this sum of the histories can be translated into when we consider this new idea of, let's say, quantum neural network. Well, exactly as you have a double slit experiment and in quantum mechanics, as you can see at the center here, and you go from a point, which is birth, okay, or input, to an end, which is death or output of your life, you can pass through A and B. So, and quantum mechanics is telling you that you have to sum over A and you over B. So you have to sum over the contribution and go to, let's say, the evaluation of the dynamics, summing over A and B. So here we have to do the same. And I mean, the idea is that while you sum through state that may represent some entry data, so the boundary condition that we have to represent, we have to pass through some steps, which are the hidden layer that we consider. And these steps are like filters, okay, that we can use. And these filters are basically processing the data. And the point is that these filters can be really thought like this double slit in quantum mechanics. In our idea, we capture everything in a graph. And a graph is powerful for several reasons. You can think graph from a very physical point of view. If you want to represent, for instance, a quantum computer as a bunch of atoms, okay, or ions. So this is, for instance, a way to instantiate a quantum computer. You have this bunch of atoms, and you have a wave function of the entire system. The atoms are disposed over a lattice, and in this case, we would have a graph, which is the initial structure, for instance, those green one, that in that case is a triangle, but for this ions quantum computer, is just a lattice, a squared point, and then you have a bunch of atoms there, okay? And then you evolve. You evolve because, I mean, you can control with your quantum gate. Basically, you can flip, spin, so you can do operation on it, and you change the wave function. So you change the wave function, you change the amplitude, you change the probability, you can maximize or minimize. Really, what you want to do is minimize an error and maximize eventually some probability to find something which is closer to your expected output. So let's say that, I mean, this is bringing also to the concept of generalization, and this is something also a work in progress right now. And we can think of generalization somehow as a limit, which is the classical limit when we recover the classical trajectory. So we go back to, let's say, some attractor, and this attractor is actually what stabilize or minimize the action. And then this minimization of the action is a concept that is naturally attained from a quantum point of view, and it somehow is going toward the quantum annealing scenario, but also the adiabatic quantum computer like processors. So why, I mean, I find everything that I'm talking to here, at least I do find, I hope that you will find also the beauty into it, very interesting. So what is interesting is the fact that there is a quantum universality. And this quantum universality is something that, I mean, it's I've been recently thinking about that with colleagues, is something that allows us to recast any kind of sequential measurement in a language which is universal, and is the language of topological quantum field theory, again, of quantum mechanics. So quantum world, the quantum mechanics is a universal language. And since we can cast everything, a lot of things in terms of sequential measurement, we can have biochemistry, we can have neuroscience, we can have, of course, artificial intelligence. and many others. So this universality also allows us, in a certain sense, to capture some points which are proper of quantum gravity. And why? Why? Because by construction we did that. By construction we started with something which is analogically described by quantum mechanics. So, for instance, our evolution from one state to the other, from the input to the output, is what in physics is called an amplitude. And this amplitude is what a mathematician called a functor. Okay, from some boundary to some complex numbers, so from state objects from a category to another category, and what in artificial intelligence is called a classifier. So basically, we have to go around many different way of naming the same things around. Okay, but I mean, if you want to picture it, it's just an evolution. An evolution among what? Among states which are graph, but this state as a graph actually can capture some property also of space-time. So you can think about this graph as the nodes were representing chunk of space. So basically these are polyhedra. And these polyhedra have as many faces, how many, basically as many links flow out or in from the nodes. And the interconnection is basically what create the structure, which is the causality structure. From a quantum information point of view, it's also interesting that these nodes are basically the point where the information flow, the information is represented by some coloring, which is assigned to the link. And this is like also a process of information. So somehow, I mean, gravity and information are share the same things. And this is also, I mean, a way to go toward the holographic projection and the conjecture. Sorry. So, I mean, now I want to switch a little bit back to artificial intelligence and show you this slide just to show that there is a way in which you can associate one of these graphs, okay? And it's very simple. For instance, take an image like that. Here there's 4 possible images of L with 3 times 2 digit, so a very simple picture. And you put at the center of this one, any one of these digits, you put node, and then you associate as many links, which are representation here, between one node and the other by taking the minimum of the color, which is the common color. So here we have 10 shades of gray. Then you associate these strands, and then you symmetrize the strands, and you construct at the end of the day a graph. And you can do that for a node, for instance, if you take this mist, for instance, sample. So this is the way in which we can associate graph. And now we can act on the graph with the amplitude of quantum mechanics or quantum field theory. And we can twist the elements. And when we twist the elements, we create information representation, but also we create something which is topologically different, we create something that encodes information. And in a certain sense, this encoding of information is very fundamentally happening also for the constituents of matter. For instance, you can describe in this way even a particle like electrons. You can describe electrons like some twisting of some flow of information which is pre-geometric, from which geometry emerge, but also matter. And the evolution that I was talking about is basically this evolution from, for instance, a boundary spin network point. Well, these are called spin network. Who invented this this word is actually Sir Roger Penrose, who is a Nobel Prize for Physics 2 years ago or 3 years ago, if you remember. And is also very much active in not only in quantum physics and the gravitational physics, but also in neuroscience. So this state, this boundary state, this spinner state evolve, and the way they evolve is through something which is a classifier for us, if we want to implement it in the quantum information, artificial intelligence, but is also a spin foam, what we call a spin foam. So a form of spin. The foaminess is the fact that, I mean, it's the evolution is spanning now too complex, and you have creation of bubble, which is exactly the quantumness that creates something out of nothing, okay? that's what's happening. So basically, you end up with something that has 3 nodes instead of 1. So you are creating complexity, and you're encoding information in this creation of complexity. Of course, it can work the other way around. You can reduce the complexity, so you can encrypt. So we have seen that there is a lot of analogy between gravity, and there is a lot of analogy between artificial intelligence. There is another way we can use this analogy, applying it directly to condensed matter physics, so to solid states. And one of the places where this things works very well is actually when we think about graphene. Okay, so these are this beautiful material which basically has been extracted in a very funny way. So basically, if you take a tape, you put the tape on, take a pencil. Okay, I mean, it's, you just, I mean, use your pencil on a sheet of paper, and I mean, it's, you put the tape, start removing some part of the graphite from the sheet, and then you repeat with another tape, and so on and so on. At the end of the day, if you do it properly, you will find that you arrive to a monolayer of atom, which has a structure which is a honeycomb structure, with the carbon atom that are at the node of this honeycomb structure. And this is a lattice, and this is called graphene, and has a lot of interesting application, because basically this, like other material that called topological material, can switch to semiconductive to superconductive behavior if they, for instance, they're subjected to some electromagnetic field, or you can also do some inject some atoms into it, and so on. So if you remove, for instance, an atom here, you create curvature. So that's why that's where the analogy, that you can fold this structure. You can remove an atom, you change the topology, but you also induce curvature in this case. And now we can think of everything like it's living on a world which is analogically described by gravity, but it's a gravity in 2+1 dimension, which is easier. And is a gravity in which, instead of having the discrete picture that I was showing before, in which the fundamental scale there is what is called the Planck scale, which is a very, very, very tiny distance. In this case, the distance is much, much larger, because it's basically order of magnitude of the angstrom. Angstrom basically is the order of magnitude of how large, okay, how big is your hydrogen atom, okay? So basically here we have 2 or 3 distances of hydrogen atom, okay? So this is how big or how small, better, are these elements. And now you can combine. You can combine in several ways. You can, if you take two sheets of graphene, you can have, because of the angle of rotation of these 2 sheets, you can have some properties that are extremely interesting. Or you can consider also graphene aerogel, which is a kind of bunch of randomly disposed graphene sheet that are interconnected among them. So these many graphene sheets can be thought as many universes that are interconnected by some chemical bridge that allows, let's say, conduction of carrier charge, basically electrons, so electric stream, among these different sheets. And of course, you can have a lot of properties, but this passage of charge is exactly the carrier that we use in order to let the flow from an initial state to an out state happen. And this flow is basically a quantum process, a quantum information process that we are then considering. So the other point is when we use nonlinear optics, and this is actually, these are other devices that has been used to create, let's say, quantum computers, and they can be used also to create circuits of artificial intelligence based on these quantum analogies. For instance, I mean, you can really think about, I mean, some photon that goes in some linear circuit, okay? But there's something in, so in some linear circuit in which you use the photons like your spin, okay? So also photon spin, of course, and you let them interact with some logic gate, which are quantum. You do some operation and you change the wave function at the end. And this wave function provide you the evolution. This wave function provide you with the classifier. Now you can think even in a more convoluted way that you can actually knot the light. So you can also create topological structure on the light. And knotting the light is something that has been achieved pretty recently in the literature. So let me end also with some system of qubit that create, for instance, quantum computers that are based on ions, as I say, trapped ions, trapped atom. So in that case, the trap happened because of electromagnetic field. But let's say that this is something that it can be attained in a very easy way with some electromagnetic field. And in this way, basically, what you can do, you can create coherence. Okay, you basically you have the coherence, so you remove the coherence with your environment. If you can put your system at a cryogenic temperature, which is very low, so that you can remove the noise. Okay, so that's with what you do, for instance, with this. And this basically this is the strategy, at the core of this quantum computer that have been constructed, for instance, by IBM or others. Now we are order of magnitude of about 100, let's say, qubit that can be put, can be entangled, and can be considered, in constructing these quantum computers. The point is that, of course, the technology in which this quantum computer relies is a technology in which you have to control all the constituents. And so you have really to have the possibility of having coherence in the system. To say that, it's the graph structure that we have introduced allow for a different way of thinking at the quantum computer, which is more, let's say, statistically also oriented, and allow, for instance, also through this, let's say, statistical behavior to rethink the problem of dealing with noise. So to rethink, of course, if you want to create a quantum computer that everyone can use, you cannot do that at the temperature which is the one of the universe without nothing around. So you have to arrive to do your quantum computer at room temperature or temperature which is achievable. So basically, it's always the same problem. It's like the problem of doing achieving a superconductivity at a temperature which is basically room temperature or close to room temperature. And this is basically what can be achieved through some topological material which are very much matchable with the topological structure that have been showing to you. So thank you very much.